and welcome to a new session of our Quantum Computation and High Energy Physics seminar. I would like to pass the word to my colleague and co-organizer Simone Mutangero for today's session.
So good afternoon, everybody. Thank you, Yasser, and welcome back to this the next Quantep seminar this series. So today I have the pleasure to introduce Professor Rainer Blatt of Innsbruck University, and of IQOCI, of the Austrian Academy of Science, that will present some of his recent work on with this wonderful machine on ion traps and related to high energy physics, and in particular to lattice gauge theory, I think. So Rainer has been pioneering quantum computation with ion traps since almost 30 years by now. He has had a lot of very, astonishing achievements, many different prizes that show how the great work that he has been doing in the last 20 years. I've seen that I've also recognized as a by that your region with the prize of Tyrolean Chevalier or something like that. So I was impressed. So with no further delay, I leave the floor to Rainer, and I'm sure we will all enjoy his presentation today. Thank you very much.
Thank you very much, Simone. Thank you very much, Yasser, for having me. This is a great opportunity. Good afternoon, everybody. And as Simone already mentioned, I'm going to talk today about quantum computation and quantum simulation of the Lattice Schwinger model. So this is specifically simulation and computation of this one, and you will see how this actually works. This is the workhorse, an ion trap that we are using. Of course, we have also more modern versions of that one, but this is the paradigm of this talk. So let me just set the stage for this. What we are going to talk about today, here's the menu, is first of all, I would like to make you familiar with the trapped calcium ions that we are using for quantum information processing. Then, of course, I'll have to introduce to you how we do things. So that's the information about the toolbox operations. And I also would like then to show you the main part of this is introduce you to this quantum simulations with spin chains. And then the two subjects that we have at hand is a digital quantum simulation, which is more computation-like of the Schwinger model, and then a simulation, a hybrid quantum simulation of the Schwinger model. If there is time, I can talk about the scalability of the issues and scalability issues here, but this remains to be seen. Just to let you know, this is all going on at the University of Innsbruck, as Simone already mentioned, in conjunction with the Academy of Sciences Institute of Quantum Optics and Quantum Information here in Innsbruck. So let's get started. As you have seen initially on the first slide, this is the workhorse, and that is an ion trap. We call this our quantum information processor with trapped calcium ions, which is a linear ion trap, which holds in the center a string of ions. And we have, of course, laser beams that we apply to these ions to cool them to that such that they line up here in the center. And we have also laser beams that can be individually addressed to these individual ions right here to do the information processing. And typically, of course, we observe this fluorescence light scattered by the ions, and we have strings available with these localized ions here, in this case, up to 20. And in the more modern experiments, we use up to 50 ions nowadays. So what is this ion? This is a calcium ion, which is a V-shaped 3-level system. So we have encoded our qubit into the two states, S1/2 ground state and the D5/2 excited state, with a lifetime of roughly about 1 second. And this is detected by shining in laser light on this dipole transition, which makes a projective measurement such that we see the ion once it's in the ground state as a bright spot on a camera for the multiplier, or if it's shelved and projected to the D5/2 state, we see nothing. So, but this is the dark part right here, which we call the logical state 0, and this is the logical state 1. And this leads to the observation of the proverbial quantum jumps, as you can see here, when this electron moves back and forth between the two states. And some people call this also the electron shelving techniques. This allows us to detect the state with as close to 100% as we actually want. It's 99.9 with several nines depending on the time you spend for the detection. Now, how is this to be written? We have this two-level system that sits in a harmonic trap. So like this one goes sloshing back and forth. So we have the harmonic ladder. In principle, we would have to rewrite this as a manifold of, say, many two-level systems sitting side by side. And there's, of course, many detunings of a laser that can be then put into interaction with these individual atoms and ions. So it's really like a molecular vibrational structure. For example, when we put the laser onto the carrier transition right here, so we connect the ground state with n phonons to the excited state with n phonons, where phonon number is just the number of the harmonic oscillator right here. Then we just address the internal degree of freedom. That's our qubit information. But as soon as we tune the laser, for example, down to n-1 right here, the system predominantly decays right here, and then it climbs down the ladder until we reach n equals 0, and that is what we call sideband cooling. Once you're in this stage, so that you're in the ground state of the harmonic oscillator, considering the motion, then you're left with 3 transitions only. So this is the carrier transition manipulating the internal degree of freedom, that's the quantum information, or you have the blue or the red sidebands, which allow you to put in or take out 1 phonon of motion. And this is actually used for the spin motion entanglement that we are using. And this is the basis for the quantum computation according to the Sirac-Sola idea. And if you want to know more about some things, here's a review that we've written some time ago. And that explains how these things work in detail. So let me summarize. The quantum information processing with trap lines can be then simply understood as running algorithms as a sequence of single qubit and 2 qubit gate operations, where each line here describes just a single qubit in time. And so we do the operations with the so-called quantum circuit model. So we interconnect these with 2 qubit gates, say, for example, of the C0 type, and I'll show you others in a minute, or single qubit operations. And all of these gate operations are then just realized by sequences of laser pulses of the carrier and the sideband. And these are, of course, all Bloch vector rotations that we know. And now the analysis is usually done by measuring the full density matrix of a state or a process. And this is, of course, done on the joint system. So we just measure or rotate prior to a measurement the Bloch sphere, measure, rotate it again in order to get the joint information on the probabilities right here. And then, of course, rotating, measuring, rotating, projecting is known as tomography. And for example, this gives you the fingerprint information, in this case of a build state, as you see here. You can also measure entanglement in a spectroscopic way via parity oscillations, but that's not the subject of today's talk. Keep in mind, what we are doing here is quantum information processing just with carrier and sideband operations. And the toolbox that we have in hand is just a summary of these operations that we do, for instance, in a resonant way by shining in the laser along the line of all of these qubits at once. So we just do collective yet local operations, and they can be done with a very high fidelity. And we do some global Milnor-Sørensen entangling gates. This is actually a 2-photon transition. You know, when you just want to connect, say, 2 states in the ground state with 2 states in the excited state, then you can do this with 2 photons, where one of them is a lower sideband, the red sideband, the blue sideband. And then you can show that, like with any 2 good 2-photon transition, the intermediate states cancel to first order. So this is independent of the motion right here, and it leads to pure entanglement between the 2 ions. This is the Milnor-Sørensen entangling gate that we're operating here with fidelities which are usually beyond 99%. In addition to that, we can point the laser to the individual ions, and then we have then the local operations, which are usually Stark shifts. And they are then together a universal gate set for arbitrary quantum computation. In principle, we have today extended that gate set by pointing even more laser beams to these individual ions, as indicated right here. So we can also do some local, what we call local Milnor-Sørensen gate operations by pointing just 2 bichromatic beams to individual ions. And if you want to know more about these individual things, I refer you to that paper right here. So again, that's the geometry. We have this global beam, and we have the local beams that do the operations and do all these unitaries that are connected to that. And for those who are more theoretically inclined, here are the unitary descriptions of the gate operations. We have the Stark shifts, we have the collective Stark shifts, we have the collective yet local operations, rotations about the generalized phase right here that depends on the laser phase. That could be anything X, Y, or in between. And we have the entangling Melmer-Sorensen gate operations, which is actually tantamount to having, say, spin-spin interactions. In addition to that, over the last 10 years, we developed further toolbox operations. Some are called hiding operations, so we can reduce or enlarge computational subspaces. So for instance, we can hide some of these lines for operations that are happening here on a global way. And we can add dephasing operations for open systems. We can initialize these operations, and we can also have a full quantum cache memory. Again, the details don't really matter, but these are the underlying operations for whatever appears then later. So the paradigm that we have for the quantum computer is then simply a number of operations. So we start from a superposition, end up with a superposition, and then we just break the algorithm in these sequence of these operations, and finally make a measurement and find, for example, one of the outcomes right here. Now, that's it. This is not a unique way of breaking down, say, an algorithm in these things. So we have come up with a compiler, which we call a compiler for multi-qubit coherent operations. And according to the author right here, former PhD student, we call this a stabilizer. And the idea is simply the following. Once we have, say, a unitary operation, as indicated right here, which is our task in order to run the algorithm, we need to break this down in a sequence of gate operations, which are a subset of these things or a repetitive subsets of these things. How to do this? And we just try to analyze this with a classical computer first by simply saying, okay, let's really try to run this unitary in such a way that we have first a set of local gates. And if that doesn't allow us to get the unitary that we have here in terms of these gate operations, we add an entangling layer and another local layer and so forth. And for whatever I show you below, we do not need more than these two layers right here, except for later on for the hybrid simulation, but I'll come back to that a little later. So in any case, this unitary is then represented from that compiler operation as a sequence of gate operations, which we subsequently apply, and that's underlying everything that we are doing. Just to give you an idea, if you have, for example, a controlled NOT operation, this is this Toffoli gate right here. This usually requires 60 NOT gate operations, but if you run it through the stabilizer as we have it here, then you can do that with 3 local operations and 5 global operations and only 3 entangling ones. Or if you have further constraints, so you don't care what the outcome is of the last line right here because you measure that, then you can save even more. So in other words, it depends on the problem, how complex the sequence of the programs is going to be. So for example, when we did the Shor algorithm some time ago, we needed to implement a so-called 4 controlled NOT operation. So one line controls 4 other qubits right here. This can be broken down in a sequence of exactly 9 pulses, as you can see here, which is not obvious. And I would not have been able to come up with that easily, but the compiler actually tells us how to do this. And likewise, if you want to do a Fredkin gate, which is a controlled swap operation, this is a bit more complicated. You see, this is a sequence which is definitely not obvious, but this can be done. Of course, that sequence, that procedure is not scalable, but it allows us to break down the problems at hand in the subspaces and in subroutines so that we can actually have the Lego blocks available to then solve our problems. Then let me come to the quantum simulation approaches that we have at hand. Now, if you have a problem to compute, say one spin problem or any many-body physics problem here, you write down your Hamiltonian. And what you usually do is you just then go to a classical computer, run it there, or if the problem is too complex, then you have to go to a quantum computer, say quantum simulator to be more general. That quantum simulator could be based, say, on atomic lattices, whatever you have there, on ions, or say superconducting circuits. And then there's essentially 3 different methods that you can use for this. The first one is what we call the analog quantum simulation. What do I mean with that? With the analog quantum simulation, you take the Hamiltonian at hand, which is to be simulated, and try to emulate it into the physics of the simulator which is being run right here, which requires then a match between the engineerable interactions that you have here and the model that you want to describe right here. But once you do this, then of course you apply that unitary that you generate from that one according to the methods that I just shown you. And then you just let it run for a certain time, and then you measure the state evolution at a certain time t and look how the system behaves. So this is a very it's a good method in order to see how the dynamical behavior of the system actually behaves. And then this is what we call analog simulation, because it's really an analog implementation of this system Hamiltonian right here. And it does not allow you to do individual error correction in an algorithmic sense. On the opposite, we talk about a digital simulation when we really try to break down the entire sequence that we have here. That is this unitary, essentially. As said before, in a sequence of unitary gate operations. So we just realize this with a quantum circuit. So this allows us then to break down the entire unitary in a sequence of these gate operations. This would allow us in each individual step to correct for errors. So this is, of course, the holy grail to get to achieve in the end. But this is, of course, much more complicated. I'll show you an example in a minute. But then there is another way to do this. This is what we call the hybrid quantum simulation. And that is known, but has been realized only recently. What we do here is the following. We just have a classical computer which holds the problem at hand. But then we allow for a quantum simulator, usually it's an analog quantum simulator, which allows us to tap into a Hilbert space. It provides the computational space. But instead of doing the computation right there in the processor, like for instance in a digital or in an analog way right here, we just want to tap into Hilbert space and produce a state. And then we make one measurement. So we do not make operations in that Hilbert space, we just make one state. And then we make a measurement. So for example, we ask ourselves, what's the expectation value of the particular problem, which then was cast by the classical computer in such a way that we have here, say, a vector of parameters that allows us to address Hilbert space in an arbitrary way. That expectation value is fed back to the classical computer, and then the computer really lets it run until we reach a steady state. Now, this is a procedure that is, of course, then easier to be applied for a steady state solution. Let me just show you examples for this one. So let's get started with the analog quantum simulations with spin chains. This is work which in our laboratory is supervised by Christian and by Ben, and works in this case with strings of ions, but here we use transversal excitations, which doesn't really matter. So it's one of the motions that we have in the system. So suppose for a minute we have a string, in this case of 7 ions, and now we come in from the side at this time with, say, a bichromatic beam. Remember, the bichromatic beam allows you to make spin-spin interactions. And if you have, in addition, say, the Stark shifts, then we have this one, the individual, say, Stark shifts right here. And as you can see here, this is immediately an Ising type Hamiltonian. This is what we can realize. And just for the sake of completeness here, this coupling matrix can be cast into an approximate power law dependence with the tunable exponent alpha, which really means alpha equals 0 means we have infinite range. That is to say that we can just connect every ion with every other one because there's, say, a common motion in the system. Or at best, we can do nearest neighbor interaction, say, with a double-double interaction like this. In practice, we can actually run this from alpha equals 0.4, 0.5 to about 2.6, but not more. But this is what roughly the range that we have available. And in this particular settings, we are mostly interested in fields which are here bigger than the JIJs. And then you can recast that Hamiltonian in the so-called hardcore hopping boson model with these X or the XY interaction that we have written down here. Okay, so let's see how the geometry looks like. It's still as before. We just come in with a global beam from the side, in this case, which provides then the spin-spin coupling with the JIJs. And we keep the single ion addressing, which is realized with an acoustic deflector. What is the kind of physics that we actually want to study? Suppose we start with all 7 ions, say with a spin down right here, say in a state that we prepare as the initial state. And then we just flip one spin. In that lingo, this is often called, we have a local quench. And then we apply the interaction. So we simulate for a certain time the radiation according to that Ising model. And then we see how these spins, for instance, propagate in this string. So we measure actually the dynamical behavior of the quasi-particle, in this case, the magnetons of the system. And here, just for the sake of completeness, this is how we actually rewrite then all the JIJs in terms of the trap parameters if you're interested in the details. What is the outcome of such a measurement? Typically, when we have, say, I numbers 1 to 7, and we have done this with up to 20, but let's just talk about 7, then we invert it, and then you see that the excitation really spreads out, and there's an interference pattern building up. Meaning that, of course, initially we start with the pure state, we create a certain amount of correlations, quantum correlations, that's what creates an entanglement, and the entanglement can be inferred from measuring the entropy by measuring the full density matrix, which we actually can do in the system by pointing the lasers to the individual lines and measuring that. Also, we can see the dynamical behavior, for example, by pointing one laser here and one laser there, and measure something, what we call the concurrence, which is a measure for the entanglement. When you do this as a function of time, then you see really how the entanglement waves are really propagating through the entire system like spin waves in such a spin chain. So this is the kind of measurements that we can do and how we can address the Hilbert space in such an analog quantum simulator. Now, what is the universal simulator with trap lines? Let me just give you that idea as well. This is what we call a digital quantum simulator, which operates now really as a full-blown quantum computer. So we just make use of the unitary that we have available. So we build up a quantum circuit. But then the difficulty is when you just have, say, a system that is to be emulated right here in the analog simulation, you really want to rebuild your system unitary now from the system Hamiltonian. But what happened if then the Hamiltonians do not commute, the parts do not commute with each other? Then you have to go to the so-called Proto-Suzuki approximation. So you just realize each individual unitary here for a certain amount of time, so time slices, and then repeat it n times. Let me just show you how this works. Again, first of all, we write down the Hamiltonian piecewise, some local system for a certain amount of time. Then we build each local evolution operators simultaneously according to the rules that I've shown you. The unitaries, remember that from the toolbox. And then we approximate the real unitary by these sequences right here. So let me give you a pictorial representation. So we just take these time slices here. So we apply laser pulses with the appropriate interactions for a certain amount of time, one after the other, depending how many sub-Hamiltonians we have here. And then that is something that we call a single trotter step or a digital time step. Then we repeat it n times, and that is efficient for local quantum systems, as was found out by the Seth Lloyd in the Hamilton paper some time ago. Let me just give you an example how this works, and then you understand easily how we can then later implement these things for the high energy physics problems. So for example, a two-spin Ising system here, this is the spin-spin interaction, this is the interaction with the local magnetic field. We write it just in a normalized notation. And then you can easily see we translate this into a Milmor-Sørensen gate operation. We translate this into the AC star gates. And for example, in this case, which of course is a toy problem that we can easily solve, we expect, for instance, two spins to point up in a sinusoidal fashion like so, and likewise two spins to point down like this. Let's try to do this in an experiment. Here we just start with 2 time slices per sequence right here, and you see this is the theory, and these are the experimental points. Their overlap is lousy, and of course the overlap can be cast into the fidelity that we want to determine how well this agrees with, and this is not very well. But we make this finer and finer. So let's just take twice as many steps, and this already gets us a fidelity of 85. And if you go yet finer, we find up a fidelity of even 91%. So these experimental points are matching the theory nicely. But if you go yet finer, then you see, apparently the fidelity does not go up anymore. And the reason for that is simply that we have now so many gate operations in order to approximate this for the Trotter-Suzuki approximation that individual gate errors accumulate, and this runs out of steam right here. So this is only something that we have to consider. In principle, that should be fine if we could implement error correction. We don't have that yet, but this is, of course, the bright future. So let me now show you what we did so far. We did open system simulations, we did dynamically phase transitions, but I want to concentrate in the remaining 20 minutes here on these two different implementations. So let's just start with a quantum simulation of lattice gauge theories which we do in a trotterized version. This is something that was done in the PhD thesis of Esteban. We've seen him before. And of course, the theory work was done by Christina Muschig, who is now in Waterloo and who did this at that time as a member of Peter Zoller's group in Innsbruck. What are we going to do? Now, the idea is to simulate such a simple QED type theory in one dimension on a lattice. It's still a toy problem, but it's just to show you how this can be done. We need to implement and encode the particles or our fermions and spins, so we use our two level systems. And the gauge fields in this case are transformed by hand to long-range interactions. I don't have the time to go through all this mathematical theory, nor I'm the right person to do this. If you really want to know this in more detail, I refer you to the paper by Christina and also to some extended information right here in that Nature paper. But I'll show you the Hamiltonian in a minute. And then, of course, we really want to realize the interaction now in a stroboscopic simulation, that is in a trotterized version. And the idea is, of course, to describe the Schwinger model, to see the dynamical behavior of the Schwinger model, that is the pair creation. So we just want to create the first step. In principle, you could go for a second step right here. Let me just move to my mouse, that's a bit faster. And this could also be observed, but we did not do this. And in this case, it's really a toy problem. We only worked with 4 ions by using the global and the addressing beam. But of course, the entire system relies on very efficient encoding. And for the efficient encoding, we use the Koga-Susskind encoding that was done and invented already in the 50s, which is also used for classical computation. That is to say, we start with a lattice where we know, of course, where the particles are residing. So for instance, we have odd and even sites. And on the odd sides, we have the particles. On the even sides, we have the antiparticles. And then we have spin up, spin down. So they could be empty, they could be occupied. And then we have a lattice spacing. And this is what's underlying the entire system. And this could be used as in a classical computer. Then we need to define our Hilbert space. For what we want to describe, we need to describe the vacuum initially. And we need to describe a particle and an antiparticle. And the Hilbert space that we use here in this case for the encoding would be the staggered state right here. That would be just the vacuum. We use staggered states because experimentally this provides what we call a decoherence-free subspace nearly, and this helps us in doing the experiments in a roughly perturbation-free way. We can talk about this in the discussion later. And then, of course, we have then here such states right here, and we have this would be the opposite where all of these things are flipped. So this would be then fully occupied. And then the question is, when we want to see the pair creation, we want to study the dynamical transition from this vacuum state to the state where we have the positron and the electron pair, the particle-antiparticle pair right in the middle, for example. What we do is we also use here, of course, post-selection. So states outside that Hilbert space are considered unphysical, though that's underlying the entire procedure. Now to the Hamiltonian. The Hamiltonian might not appear to be familiar to the high energy physicists who are used to doing this in a lattice gauge theory, but this really can be rewritten, and this is written in this paper by Christina right here, in such a way where we transform the gauge fields in such a way that they are encoded into the interactions, and we end up with a Hamiltonian that can now be implemented on such a quantum computer that's a spin chain quantum computer. This leads to the fact that we have here, of course, the particle-antiparticle creation annihilation part, but we have here, of course, then appearing a long-range interaction, in spite of the fact that, of course, the Schwinger model is not long-range, but this is sort of artificially appearing, and we have the effective masses, which have a correction term, which comes from this transformation. And then, of course, here the numbers here, the interaction, lattice spacing, and so forth are the same. But keep that in mind, this is the Hamiltonian to be implemented. Unfortunately, the GIJs, as they come out from this transformation, appear to be asymmetric. And here comes the good part, of course. No matter what, this is something we can do in our quantum computer. We just have to program the quantum computer accordingly. And this is done in the following way. So we just have 3 parts. See the color coding of the Hamiltonian right here. And this color codes brown, red, and the ochre part right here. Yellowish part, there are the 3 Hamiltonians, and we want to repeat them in a trotterized version. So let me concentrate here on the 3 different parts. This is CC term, the long-range interaction. This is the creation and annihilation part, and this is the mass term. This can be done efficiently with Mimosensing gates operation, which we apply between adjacent and some other ions right here. And then this is usually done by the Stark shifts and so forth. So we can really implement in the unitaries as said before. Then we come up with a compiled pulse sequence, which allows us to initialize things. So we prepare the vacuum state. That's the typical spin state that I've shown you before. And then we break down the entire sequence of these Hamiltonians into these three parts. This is the creation and annihilation part. This is the mass term, and this is the long range part, which is a bit more complicated, but we can do this. And finally, we have a trailing recoupling sequence, which allows us then to measure the appropriate basis, then again to get the result. And keep in mind that we have to repeat the Trotter sequence now several times, in this case 4 times, until we get the result. What we do here, we have already run then the quantum computer with 222 gate operations, not counting for calibration pulses. Now, what do we see? We want to study the transition, the pair creation from this vacuum state to this state where the pair is here in the middle. And if we do that, then the theory, of course, tells us this should look in a sinusoidal fashion. And if it would go on, then we could create another one. But let's just concentrate on the first part. Then when we do the measurements are shown here in purple. And if we look at these things in detail, then we see, of course, that deviates slightly, at least for many more applications right here. What is the reason for that? If it was just a discretization error, then we would just get the red points, which is the discretization from the Trotterized version. So we would have to go to finer slices. But then, of course, we would have too many operations. So we at this time, we already have some deviations because we have an error model that is just polarizing noise, depolarizing noise. And in taking that into account, this is such a simple depolarization that we have here, we get pretty well agreement with what we actually observe. So this essentially what we observe here, we start out with a vacuum and we create that state right here in the center with these particles at this point. This is then the pair creation, which we just saw in this case and demonstrated in the quantum simulation. We can do this in a wider way. We just take a mass as a tunable parameter, take the interaction, and we can map out essentially experimentally all these parameters here, where we just have the particle number density defined in such a way that 0.5 here is just one pair. But let me conclude here this part with showing you some results. What you're actually doing here is, of course, you create a pair, and this pair originates from a single point in space. So in other words, they are heavily entangled. And the question is, can we measure that? And also, how does the vacuum persist? So this Low-Schmidt amplitude right here shows you how the vacuum survives in the system. So here would be the Low-Schmidt amplitude squared, or the probability for the vacuum to survive. The vacuum breaks down, and then you create particles and things like this. And you go for the mass dependence and E-field dependence. You can also do these things in detail, and they all match precisely what we expect from theory. So you see the theory and the experimental points are overlapping. And moreover, we can actually see that we create an entangled state, because from the mapping, we know that the pair is appearing in the center. So we just take a bipartition, which has a border right in the center. And from the negativity, from the logarithmic negativity, we can immediately confer that there's entanglement appearing. So the simulation actually gives you access to these things. I understand that this is, of course, nothing that is yet to be applied to high energy physics problems, real world problems, but it shows you how to implement these things in the toolkit case of that we have here. Let me go on and show you some more recent results where we now applied this in a hybrid way. And this is work that was theoretically done in the group of Peter Soller, Tariq van Bijnen, and Christian Kokeil. And this is the experimental work was done by Christine Meyer in her PhD thesis over the last several years. What is this about? As I showed you before, the goal is here to prepare, for example, a steady state. In this case, say the ground state of this Hamiltonian, of the Schwinger Hamiltonian in this case, by minimizing the measured expectation values in this case. And we do this by formulating the problem in a classical computer, which thinks about the parameters set to tap into the Hilbert space of the quantum computer, or the analog quantum simulator in this case. There we measure, say, an expectation value, feed it back, and let the system go. The big advantage is here that the hard part, the target Hamiltonian, lives only in the classical computer. So we don't do a full-blown quantum computation. We just make use of a Hilbert space that's provided by the quantum simulator right here. And the feedback loop between a classical computer and a quantum coprocessor then leads to a steady state result. How does it work? Again, we break down the Hamiltonian in the sum of Pauli products in this case, because that's what we can implement in the system. This needs to be done and reconfigured. And then, of course, in the classical computer, we can just reformulate things and measure then with these correlators the expectation values. So the classical computer thinks then first of a parameter set, hands them over to the quantum simulator. In the quantum simulator, we have to reach every nook and cranny in the Hilbert space, which is necessary. So for this, we need a certain sequence of steps in order to really reach every state in the Hilbert space. And this is the number of parameters that we actually use for that. So we have thetas. These are phases for the entangling operations, phases for some local operations, phases again for entangling operations, and so forth. And finally, we have to return to our measurement basis with some local operations and take a measurement. And the measurement then feeds back an expectation value right here. And this is to be compared then what we calculate from the correlators that we measure right here with what we expect in the classical computer. Now, then this goes around and around until we find a steady state. How does it work? Again, here's the Hamiltonian, again, a slightly different notation, but otherwise the same Hamiltonian and the Koga-Susskind notation as before. And we just use the same problem again. It's about pair creation or whatever you do. You just want, in this case, to study there is a ground state and not the dynamical behavior of the system. For this, of course, we need some resources. As said before, to tap into the Hilbert space, we have a sequence of these operations. For the sequence, we just use our operations that we have from the Ising model. So this is the XY operation that we had before. Then we have single qubit operations, the Stark type, and we have the collective operations. And what we do on the next few slides is we just make use of, say, up to 15 parameters, which are set by the phases here in the various operations, where we use some symmetries here of the system. So this is 1, 2, 3, 4, 5, 6, 7, 8, and so forth. These are these three are the same as this one. So this adds up to 15 in the end. How does it look like? Initially, we talk about 8 ions and 10 parameters here, and for the Lattice Schwinger model Hamiltonian. And how is this to be read? This is what I call sometimes a fly sheet program because of all these gray points right here. This is an expectation value that we measure, and this is sort of the iteration history. We start out somewhere, the classical computer finds a parameter set theta, and we measure the expectation value. Then the computer thinks, oh, I have to iterate this, and runs it again and again and again. And then we find slowly convergence. But of course, in a multi-parameter problem like that, you have lots of local minima. So you add a stochastic component in your algorithm, which adds then these measurements points in between. But eventually, we find then the ground state, which we, of course, calculate in this case for theoretically well. The idea is to iteratively determine the energies. But of course, and this is much more important, you can also iteratively determine the error bars from the variances, because the ground state can be inferred from subspace expansions and things like this. And then you can just measure the differences right here squared, so the variances. And that gives you access to the information on whether you have reached already, say, a steady state or not, because this should vanish for any eigenstate. Or you could also go for the first excited state. And you see, this is what we call the exploration phase of the search algorithm. And this finally then the refinement phase of the search algorithm. And if you do this now for a full-blown 20-qubit register, the sequence looks like this. So we just have here the energy that we find, and then we can estimate after the outcome what the ground state energy is going to be. And these, of course, are the error bars, and this is what we finally get there. One big question is, of course, when do you stop doing this? What is the real minimum energy? Usually, you just go only for so long until you have exhausted your resources. We know, of course, here what the energy is because we still can calculate that. And we can see here the fidelity, which goes up to about 85% in this case. Principally, we would have to go on until we really reach the ground state, but nobody knows how long that's going to take. This is the downside of this algorithm. So this is essentially then the outcome of this. And how well does this agree now with the theory? The theorists around Peter Zoller were able not only to evaluate this, but they were also able to run and simulate everything theoretically. So we have for each measured result also a simulated result and can compare this. And you see here the correlation, and you see this very well agrees with what we observe. So 55% are within 2 sigma of these points. So we can rely pretty well on the quantum simulator approach and the hybrid simulation that we have. And if you do this and look for the search landscape, then of course we have to worry about, is there anywhere, say, a local minimum? And yes, there you can find local minima. You have to worry about this. This would be one of them, but you have to run it long enough, and then you find eventually it settles down there. And from this, you can actually evaluate also the fidelity, how well this overlaps. Question then is, how much can you trust this experiment? And for this, we resort to measuring again the variances. That is actually measuring the closeness to an eigenstate, which is a bit more complicated because you have to measure now this difference squared. So you first of all have to measure, say, the ground state energy, or you have to conclude it. You're not allowed to calculate that because then you have solved the problem anyway. This can be done with experimentally with the so-called subspace expansion, and there's some information available. If you really want to know more about this, you find more details here. So you can put this in, and then you can determine the variance. And if you do that, you have to measure this, of course, in various bases, and the measurement efforts are a bit higher than just measuring the expectation values. So in order to do that, you have to run this on many more bases. So this is why we resorted to doing this only with 8 ions, with 20 ions. This would have taken a little bit too long in the first phase. Maybe now we can do it again. But the bottom line of that one is, if you just compare again experiment and theory, they are really right on top of each other. And eventually, the error bars are smaller than the gap width from the ground state. And this is important, which really means that we are now within the error bars really at the ground state, and the error bars are small enough that we can say, yes, we have found within our experimental limit the ground state that we have here. One final thing that we can also study in such a phase and in such a system is, of course, a prediction that was done some time ago. The Schwinger model is supposed to exhibit a phase transition. What does that really mean? Now, take your register. If the mass, for example, is very small, then of course the energy is required to generate the pairs is very little. So you expect that for small masses that the system is fully occupied. But whereas if the mass is very high, say on the right-hand side right here, it requires an enormous amount of energy to create this, the pairs. So in other words, when you just change the mass, which of course you can't do experimentally, but in theory you can, then you would expect a phase transition like this. We can measure these things, and we can also verify that we have a huge amount of entanglement in the system. Here we just verify this by measuring the occupation here of the lattice size, which is given by these expressions right here. And you see the phase transition right here. And what you also can verify is that there's a huge amount of entanglement here, because the amount of disorder of the subsystems really goes up quite a lot, as you can see here in this lower curve. This was measured by measuring the Rayleigh entropy. This is a particular protocol that was also developed by Peter Zoller's group and implemented by us also in 2019. And if you want to know more, I will refer you to that science paper. But just importantly is because you really require to measure these points. They are differently colored right here. You require, say, a very precise measurement, or say a simulation, tapping into the Hilbert space. So the layers are, instead of using 4 layers down for all these numbers right here, we used 5 layers for these points to reproduce these points. And then you can see actually the entropy rising and showing you the entanglement. Let me just briefly summarize this variational quantum simulation part. The quantum system here does the hard part, but the classical computer does what it can do best. And so there's no need to generate the Hamiltonian right in the quantum computer. You just have to tap into it and into the system and run it in cycles. There's no specific quantum resource required except for this simulator. So it is actually a very versatile tool. It's scalable for some interesting problems. There are some scaling this scalability issues, and there are some ideas how to do things, and we have put this in our paper. But the downside of this, it needs very many repetitions. So in order to really make use of that, you have to run it very often. So in other words, in the future, we will need faster experiments. We will have to speed up all the feedback loops. And of course, in the end, we will have to run this for a larger number of ions. And we are currently gearing up to implement already 2D models, because in 1D, I think things are fairly trivial on the classical computer, but the interesting things begin in when we have a 2D model available, which we are trying to do in the near future. With this, I'm already near the end of my talk. Let me briefly summarize. The future goals and developments are such that we have
Rainer, since we have lost you.
Hello, Rainer, can you hear us?
Seems we have some connection problems. Oh.
So it seems, okay. Rainer, are you there?
I'm still here. Sorry for that. Did you lose me?
Yes, when
Yes.
you were starting your last recap slide. But so
Yeah, so let me just go to that one, and then we can recap things. I apologize for this. Okay, so this is the slide that you.
Yes.
This is the one?
Yes.
Okay, let me just repeat. What we need to have, of course, in order to get to interesting problems, we need more qubits. And when we have more than 50 qubits, then this really things become interesting to the point that the classical computers probably won't be able to calculate that anymore. But for this, we also need better fidelities. We need faster and more gate operations. So we have to go to cryogenic traps, microstructure traps, as you can see here. This is already a trap that we developed jointly with a chip company Infineon, and we are getting there to get things more reliable. Of course, in the future, we are trying to develop, say, two-dimensional trap arrays and some electronics right on board to do these things. But there's still a problem remains. The larger the system is, the more difficult it gets to characterize, say, entanglement. And for this, we are developing also routines. But the key problem and the holy grail to achieve is what I call keeping the qubit alive for the computation. And this will be done by the implementation of error correction. That's a big program in our group and worldwide. And we have done bits and pieces of that, but we still need to put everything together. This is this project right here. And I think we are getting close, but it's not there yet. But once this is done, everything else here, the applications on repeaters, metrology, simulations, computations, that's going to be not easy, but it's doable, because then we have enough operations available. Let me conclude by just showing you that this is a large team, and of course this would not be possible without the support from all of these theorists, in particular, of course, Peter Zoller's group or Miguel Ángel Martí Delgado's group for error correction and things like this. Then here are the names. Then just to show you where we are, this is Innsbruck in springtime, and this is the airport, and right here is our institute. This is the home of quantum computer made in the Tyrol. And if you want to buy one by the end of this year, we should be able to provide you with one from Alpine Quantum Technologies. So bear with me. And this looks simple as that. This is just two 19-inch racks which house everything from the ion trap to the control units to the lasers, whatever you want. And this does not even need more than a kilowatt of power in order to run it. And so this should be affordable to many institutions. For this, we have everything put inside, and the person in charge is, of course, Thomas Mons, who is the CEO of the company. And if you want to know more information, just contact him and buy one. This is AQT, the quantum CPU, the CPU of the future. I hope you enjoy this as much as I still do enjoy the research here. And if you have questions, I'm available. Thank you.
Thank you very much, Rainer, for this very fascinating talk. A virtual applause. And so I remind all the audience that you can write your questions in the chat on the YouTube channel. There is some second of delays, so be aware of that. But I see we already have one, so I will read it to you, Rainer. So that is from Javad Kazemi, which asks, could you elaborate on dissipative operations in terms of their experimental realization in trapped ions and whether they are controllable enough to be used in variational quantum simulation?
That's a good one. Thank you very much. We have done this so far. This is, of course, relying on the controlled optical pumping. So we can just use, say, very short pulses to introduce some dissipative operations, and then we do get spontaneous emission in the process. This has been used in order to generate Bell states, GHZ states, and the like. So we can produce in a dissipative way non-classical states. Whether that can be used for quantum simulation remains to be seen. Most likely, it will be used for the preparation of the initial states in the variational for a variational calculus. During the operation, I doubt that this is very helpful because it needs to be, you can control it, that's not the point. But I have no idea, and this would have to be pointed out, where it could be useful in an algorithm. It definitely is useful in the preparations of the initial states.
Thank you very much. Then there is a more practical question by Vladimir Korepin, which asks, what is the cost of your quantum computer?
I think that that's a very good question. I would like you to, I would urge you to address this question, to discuss that question with Thomas Mons. I think we can certainly provide you with a full-blown quantum computer, as I've shown you in the two cabinets and 19-inch racks, but we're also selling modules, say parts of that.
Okay, good. Thank you. So then, yeah, here from Sagar, who is curious and asks, but you have spoken about two-dimensional implementation in the near future, and is
Yes.
wondering if you can expand a little bit on that. What is the status and what are the biggest roadblocks?
The status on that is the following. We are collaborating for this with Christina Muschig again, who is now at the University of Waterloo, and she has already cast at least the calculation in a Hamiltonian that we can implement, and this is a so-called ladder approximation. So we are sort of meandering to a two-dimensional problem in order to really address this on a linear system. This works at least in an approximate way, and at least from what we can see on a classical computer. So the algorithm is there and the procedures are there. We need a few more ions than just the 4. I think with 10 or 12 ions, that's the minimum that we need for this. We can actually do this. And we will see how this goes. And at least what we are doing, the status is that at this time we do classical simulations on a classical computer before we actually embark on doing this on a quantum computer, because we need to know where this goes and what to optimize.
And I would be very happy to see 2D quantum simulations. And now we have some tools to classically simulate those systems as well. So it would be very nice to compare results as soon as we arrive there. So we have another question from the audience. Duarte Magano asks, what is the status of your effort on the simulation of non-abelian gauge theories?
Again, this is one step further, and again, there's ideas. We are working for this with various groups. Again, also with Christina Muschig and of course the Peter Zoller group. This will take a little while longer. As a precursor to this, we are trying to study some Haldane physics first, which also requires some of these operations here. And this is not completely clear whether we can use, say, fortuitously Q trits instead of Q bits. this is something we are investigating. It's at a very early stage, but of course, this is along the lines that we are thinking.
Thank you very much. So I don't see any other urgent questions, and I know that you have other commitments that soon are coming up. So I would thank you very much for this talk and for all the things that we are sure you will show in the next future. So thank you again. And I pass over my...
We are carrying. Thank you very much. Thanks for having me.
Thank you. So yes, sir.
Thank you very much, Simone. Thank you, of course, Heiner. It was great. And I just wanted to thank everybody and announce the next seminar, which will be by Simone Montangero, co-organizer of this QuantTap seminar, and he will be talking about high-dimensional lattice gauge theory simulations at finite density with unconstrained three tensor networks. So thank you very much, especially to Heiner and to everybody who participated, and see you next month. And thank you, of course, to the co-organizers, Andres and João, and also to Rafaela and Sagar, who made this electronic seminar possible. Thank you, everybody. See you next month. Bye-bye.